Good evening, everybody. So, today we will see how the different metal complexes are forming and what type of interactions we are talking about so far, where we can consider a particular metal ligand bond. That means the nature of the bond, which always plays some important role, because once we have the metal ion, it can form with the ligand, whether the ligand is a neutral one or anionic one, it can form the corresponding bond. And this particular nature, what we all know now, that it is basically a coordinate bond, where both the lone pair of electrons, if they are available on the L, they can be donated to the metal. So, both the electron pair which is forming that particular bond are coming from the ligand itself. So, not only the formation of the bond, it can be more than one, because we know that a particular metal complex can be formed depending on its coordination number and preference of that particular metal ion. So, if it is forming 4 such bonds, we get a corresponding Ml4 species. So, the nature of this bond, the type of the bond and the strength of the bond is basically also reflected when we talk about the corresponding removal of this bond or the breaking of this particular bond. That means the bond dissociation. So, this bond dissociation would also be very much important, because in that particular case, if one L dissociates, we will end up with a species like Ml3, or sometime we get the formation of new compound by the addition of 2 more ligands, such that this particular M can immediately be converted from a square panel geometry to an octahedral geometry. So, knowledge of the type of the bond is always very much important, the way we know for the different covalent compounds, like the formation of the methane molecule from carbon and 4 hydrogen atoms in a particular tetrahedral geometry. So, this tetrahedral geometry will all the time tells us that we have the carbon center, and that particular carbon center is attaching, forming 4 CH bonds. Similarly, a metal can have same type of geometry. We all know that this can be obtained like species FeCl4 2 minus. So, here also we have 4 such FeCl bonds compared to 4 CH bonds. So, the organic chemistry mainly relying on how good we are handling the corresponding methane molecule and how we can break the corresponding CH bonds. So, CH bond breaking process as well as the new CH or CC bond making process, always we talk about in these in typical organic chemistry synthesis reactions and mechanisms. Similarly, in coordination chemistry, if we consider the formation of this Ml4 species and its conversion and its reactivity, all the time we should focus our attention on the nature of these bonds. So, likewise, if we see that FeCl4 2 minus compound is also tetrahedral in geometry, and we have 4 such official bonds. So, how we get the corresponding species? Because we know that this particular molecule is forming through some hybridization. The hybridization concept was introduced in the time when people are talking about how the electron pairs are shared between two atoms during the formation of the covalent bond, and the same hybridization concept was extended towards the formation of these metal complexes also. So, in this particular class where we will be talking about bonding in complexes, so we will be very much interested to know how the hybridization concept can be introduced in dealing with the corresponding bonding nature of the metal ligand bonds. Because these bonding theories are very important, starting from the very simple chemistry what we all talk about, because we have to explain the color and magnetic properties of different transition metal complexes, how this color is originating, the pink red color for cobalt 2 plus when we dissolve any cobalt 2 salt in water, or nickel 2 plus when we dissolve this nickel salt, nickel chloride or nickel sulfate in water, and the blue color of the copper 2 plus in water medium, and the zinc in aqueous solution. So, in all these cases we all know that whenever we dissolve any nickel salt in water, the preference for that particular nickel center is that it will immediately bind 4 water molecules taking from the medium, and they are the ligands in the metal complex, that hexa-echo complex. So, we have the hexa-echo complex, and this particular species which is forming in solution, we have to explain the color, how the color is originating from this particular species what is forming immediately in the solution. Similarly, for other metal ions, when the zinc is also colorless, that has to also be explained why the zinc is also colorless. And if we go further taking this nickel solution, and these are not well matched colors, or the colors are a little bit different because this nickel hexa would be green in color, and the bluish coloration of the hexaamine compound and the corresponding darkening of the tris-ethylene diamine nickel compound can also be explained from a typical bonding theory that we all expect. So, this particular color what we all know now, that this can be related to the wavelength of the light which is absorbed by the corresponding compound or the corresponding solution. So, why this is colored blue? Because it has a strong absorption band in close to 510 nanometer. This is in the nanometer scale, and this particular case it is the corresponding absorption. So, this particular part of the electromagnetic radiation, that means the greenish part, is being absorbed. So, this part when is absorbed, the corresponding color what we will be getting as the corresponding solution color is the corresponding emitted color, because in the ground state we have some electronic transition to the excited state when the corresponding h nu as the radiation is absorbed, and we can calculate out the corresponding energy gap, which E1 minus E2 is the corresponding energy gap as delta E, and that energy gap corresponds to a h nu value, and the Hc can be calculated, and the lambda value can be found out for the corresponding absorption. So, we should have some idea about the gap between the ground state and the excited state for a corresponding color what we will be getting for a corresponding compound in solution. So, if we can have a corresponding bonding theory for the metal and ligand interaction, such as the interaction between the metal center and the water molecule itself. So, how we can modify this interaction of OH2 where water is the ligand, then Ni2 plus with ammonia, water is replaced by ammonia, and then the interaction with the bidentate chelating ligand ethylene diamine. So, the color is changing from one solution to the other, and the interactions related to the corresponding bond, which is NiO, NiN and NiN. So, depending upon the corresponding environment for the complex formation and the nature of the bond, how we can consider that when the corresponding octahedral compound is forming, the octahedral complex formation is taking place, and how the corresponding electronic transition can take place between E1 and E2, which can give rise to the corresponding color of this particular compound. So, the formation of methane molecule or any other organic compound was first proposed by Jean Louis in around 1902, and in there Jean Louis has that idea that the covalent bond can only be formed by sharing of electrons between the two atoms. So, before the advent of the quantum mechanics and any other sophisticated theory, this particular aspect of the formation of the covalent bond in the hydrogen molecule also was proposed, and that particular hydrogen bond formation can be conceived as if we have one electron from this hydrogen and the second electron from this hydrogen, and both these two electrons are shared. So, this was the proposal from Jean Louis for the corresponding electron pair sharing between two atoms for covalent bond. But Walter Heitler and Fritz London around 1927 showed that the sharing of pairs of electrons holds a covalent molecule together. So, this sharing is very important, and when the sharing is taking place, we can have the entire molecule and we do not have the corresponding atoms separately. So, when we consider the hydrogen molecule, we definitely have the corresponding hydrogen-hydrogen bond, and the hydrogen molecule has the corresponding hydrogen atoms, they are bonded together. So, that basically gives us the corresponding idea that the electron pairs are localized and those electron pairs are shared between the two atoms, and the two atoms are being held together for the formation of the corresponding molecule. Similarly, the formation of the methane molecule as well as the formation of the Ml4 species, where we see that one particular Ml bond is forming through the sharing of electrons. So, this model, which is known as Heitler-London model of covalent bonds, was the formal basis of the formation of this corresponding valence bond theory in metal complexes. So, we will consider this as the VBT, which is valence bond theory, and these ideas can consider for the corresponding bonding pattern in the metal complexes. And around 1930, it is Linus Pauling who originally proposed for the different bonds and the nature of the corresponding chemical bond also, where he utilizes the hybridization idea, the concept of hybridization. So, hybridization of suitable orbitals, because we all know that whenever we have the metal ion or any other atom, we can have the corresponding orbitals. So, we can have the corresponding s orbital, we can have the corresponding different p orbitals and different d orbitals. So, these orbitals when they involved in hybridization, so this idea was mooted that time for hybridization. So, hybridization of suitable orbitals not all orbitals are being involved for the corresponding hybridization between these atoms for getting the corresponding bond. So, if we have a metal ion and that particular metal ion can have more than one type of orbitals. So, we take only the suitable orbitals of the metal ion can go for the corresponding hybridization, and this particular hybridization can give rise to the desired stereochemistry. Desired stereochemistry. Because now we all know that when a methane molecule is forming CH4, it has a tetrahedral geometry. So, the sharing of the electron pair for the formation of the 4 CH covalent bonds will give rise to the corresponding methane molecule as a tetrahedral molecule, and the hybridization is sp3. That means one s orbital is mixing with 3 p orbitals, giving rise to 4 hybridized orbitals on the carbon atom. So, on the carbon atom we can have the corresponding hybridized orbitals available. Similarly, for the corresponding hybridization on the metal center, if the metal center is that particular iron center, and if we can have the similar type of hybridized orbitals what is available for the formation of methane, so they are available as for the methane. So, these orbitals like these on the iron atom is also available there. So, these are the typical sp3 hybridized orbitals. If we get those hybridized orbitals in a similar fashion, the way we get the corresponding methane molecule, then the ligands with lone pair of electrons will come and overlap with these hybridized orbitals of the metal center, such that we can have 4 FeL bonds. So, these 4 FeL bonds will be present there within the complex which is FeCl4 2 minus. So, FeCl4 2 minus molecule will have 4 such FeL bonds, and this is due to the corresponding hybridization scheme proposed by Linus Pauling. So, that time he proposed that atomic orbitals from the corresponding atom of the metal ion mix to form hybrid orbitals, such as what are the different types of combinations possible. So, these combinations are sp for mixing of 2 orbitals s and p, giving rise to a linear orientation, and that linear orientation we all know now that linear orientation means that if we have the sp orbitals, that means mixing s with p giving 2 sp orbitals. So, these 2 sp orbitals, if we consider it is on the silver ion, so this will overlap with the nitrogen atomic orbitals of ammonia molecule, giving a linear molecule of AgNH3 whole 2 plus. This silver is plus. So, like that we have this sp hybridization for the corresponding AgL2 molecule. Similarly, we can have the corresponding sp2 hybridization, dsp3 hybridization and d2sp3 hybridization for the typical orbital. So, when d2sp3 hybridization is taking place like sp hybridization, we are mixing two d orbitals, 1s and 3p orbitals. So, altogether 2 plus 1 3 plus 3 6 orbitals we will have. So, why we need 6 orbitals? Because these 6 orbitals are required for the corresponding octahedral stereochemistry. So, if the stereochemistry is controlled for the formation of the corresponding octahedral compound, we must have 6 hybridized orbitals which are coming from 2d, 1s and 3p orbitals. So, this valence bond theory therefore predicts the metal complex bonding which arises from overlap of filled ligand orbitals and vacant metal orbitals. So, these hybridized orbitals what are forming over there like sp3 or d2sp3 or sp3d2 type, they are all vacant. So, they are the hybridized vacant metal orbitals. So, we must have first the hybridized vacant metal orbitals, and those hybridized vacant metal orbitals can overlap with the filled orbitals of the ligand. So, ligand can donate the electron pair to the metal orbitals, thus forming the corresponding metal ligand bond in a usual way as the coordinate bond, or we can consider this as coordinate covalent bond. So, when a complex ion is formed, each ligand donates an electron pair to the metal ion. So, each and every ligand will be utilized for donation of electron pair to the metal ion during the formation of the complex, and we will be getting a corresponding coordinate covalent bond. So, the resulting bond is a coordinate covalent bond. So, we will be getting a corresponding coordinate bond which is due to the overlap of orbitals of metal and the ligand. So, if we have this vacant metal hybrid atomic orbital, so on M it can be one of the hybridized orbitals, say sp3, sp2 or d2sp3 type of hybridized orbital. So, this is one of the shape of one of the vacant orbital which is utilized for making the corresponding overlap with the ligand orbital. So, ligand has the corresponding occupied orbital, and the occupied orbital can have the corresponding electron pair in this orbital. So, this Ml bond will be forming and the electron density will be localized between M and L. So, Ml bond will look like this, and we have both the electron pair which are coming from the L, the ligand will now be localized between M and L. That means both the two electrons can have now the control by the metal center as well as the ligand center, though they are coming entirely from the ligand only. So, this theory therefore considers that the overlapping atomic orbitals of the participating atoms form a chemical bond. So, how we consider a chemical bond? So, we have the overlap and two atoms, that means the metal atom and the ligand atom are involved, and they are bonded through a chemical bond, and they are engaged in more than one chemical bond to get a corresponding metal complex depending upon their coordination number. And in terms of this theory, the filled orbital of the ligand overlaps with an empty orbital of the metal ion. So, this is the idea, and this idea also tells us that the ligand is there and both the electron pair from the ligand will be donated to M. and once the bond is formed, we just simply write is Ml. So, we will not consider or will not think of that both the ligand has been originating from the ligand only, because these two electrons will now under control of both the metal as well as the ligand. So, the metal will have the share of this electron and the ligand will also have the equal share for that electron. So, the valence bond model proposes that the geometry of the complex ion depends on the hybridization of the metal ion. So, Linus Pauling proposes the different types of these hybridizations, and depending upon the type of hybridization, whether it is sp3 or dsp2 or d2sp2 or d2sp3, we can have the different geometry for the metal complexes, because the three dimensional complex we can have so many geometries possible for all these metal complexes, which are not so in number in case of the corresponding organic chemistry centered on carbon. Because in organic chemistry the carbon center can have only the tetrahedral geometry, but in case of metal complex, where we have seen earlier that depending upon the coordination number say 4 or 5, we can have the different geometries. So, as we have different geometries, we can definitely have the varying hybridization scheme. So, we must have the varying hybridization scheme to accommodate the different number of ligands around the metal center. So, the atomic orbitals for bonding may be hybrids. Often the bonding orbitals have a character of several possible types of orbitals. The methods to get an atomic orbital with the proper character for the bonding is called hybridization. How we get this? So, this particular methodology, where the different atomic orbitals of the metal center, say 1s or 3p orbitals with proper character, that means one having s character and 3 having p character, are utilized for bonding. So, it is not the pure S or not the pure P which are being utilized for bonding, because we need a particular geometrical orientation. The stereochemistry of the metal complex is different, which cannot be explained by taking the idea that only the p orbitals are involved in bonding or only the s orbitals are involved in the bonding, but the hybridized orbitals are involved in this particular type of bonding. So, if we see a particular geometry for the tetrahedral complex like cobalt Cl4 2 minus. So, the number of unpaired electrons which can have on this particular molecule is important, because once we make this compound, it can be the corresponding potassium salt, it can be the corresponding ammonium salt, or it can be the corresponding cesium salt as well. So, depending upon the nature of this particular salt, the complex species is COCl4 2 minus, and it has 3 unpaired electron. So, we can have the corresponding unpaired electron on cobalt, which is in +2 oxidation state, that means its electronic configuration is 3d7. So, 7 unpaired electrons are there, and we are having a geometry which is related to sp3 hybridized orbital. So, all these 7 electrons will be distributed among the 5 levels of the D, and the number of unpaired electrons can be counted from there, considering that these orbitals which are utilized for the formation of this tetrahedral molecule is not connected to the D level, it is only the S level and the P level. So, this is the corresponding shape of the cobalt tetrachlorocobaltate anion. So, if we have the tetrachlorocobaltate, it is 2, oxidation state is 2. So, tetrachlorocobaltate 2 ion, and it has, since it is cobalt 2 plus, it has corresponding electronic configuration is 3d7. So, 5 d orbitals are available to accommodate the 7 electrons. So, these are 3d, all 3d, then 4s and 4p. So, if we have the corresponding hybridization utilizing this sp3, we will have the corresponding hybridization like this, where the sp3 hybridized orbitals, they are 4 in number, 4 sp3 hybridized orbitals will have the electron pairs. So, initially they were vacant and they are coming from the Cl minus. So, Cl minus, 4 such Cl minus around the cobalt center are donated to these particular sp3 hybridized orbitals. So, the remaining 7 electrons which were originally present with the cobalt center, that means it will have the same free ion electronic configuration. So, the remaining one, that means the 7 electrons, these 7 electrons, 5, each one is occupying 1 first, then the pairing. So, we have 3 unpaired electron, which is same as that of the corresponding free ion value. That is why we consider the compound as paramagnetic, will be attracted by the magnets also. So, 3 electron paramagnetism can be explained at this particular point when we consider the corresponding hybridization scheme. So, this particular compound will be 4 coordinate and tetrahedral. So, this basically gives us the beautiful hybridization scheme for the formation of 4 cobalt chlorine bonds around cobalt. And we have the tetrahedral ligand arrangement. So, this is the tetrahedral geometry, and the cobalt center will have 1, 2, 3, 4 hybridized orbitals. So, these are the 4 hybridized orbitals, sp3 hybridized orbitals, which are so disposed that they are occupying the corners of a regular tetrahedron. If we conceive this tetrahedron within a cube symmetry, within a cubic symmetrical arrangement, then alternate corners of the cube will be occupying by the 4 ligands. So, Ml4 species, so this chlorine, this chlorine, this chlorine and that chlorine will be occupying the 4 alternate corners of a regular cube geometry. So, we have 4 hybridized sp3 orbitals available on the cobalt, and they will overlap with the corresponding filled chlorine orbitals for the donation of 2 electrons to these cobalt hybridized orbitals. Therefore, what we get cobalt 2 plus as sp3 hybridized molecule in tetrahedral COCl4 2 minus complex ion. So, cobalt 2 plus will be there and will have the tetrahedral geometry. Similarly, cobalt 2 plus can give series of compounds. So, once we know one particular cobalt 2 center, we should also have some idea about the other cobalt compounds in +2 oxidation states, such as tetrathiocyanate cobalt 2 also. So, then you can have the cobalt tetrabromo compound and the cobalt tetraiodo compounds, all will be therefore tetrahedral, and they all will be paramagnetic, and they can have 3 electron paramagnetism supporting the regular geometry through sp3 hybridization. But what happens if we have the corresponding nickel in +2 oxidation state, because we know that reaction of nickel 2 plus with Cn minus give rise to this particular NiCN4 2 minus complex species. Now the hybridization scheme is different, which is DsP2. So this DsP2 hybridization for tetracyanonickelate compound is such that, which is square planar, therefore that 3d x square as y square. So one of the d level is now utilized for hybridization, then 4s is utilized, 4p of 2, of the 4p levels, that means x and the y, giving rise to a hybridization scheme for DsP2, which is therefore 4 coordinate again, but is completely different from the tetrahedral geometry. Which is 4 coordinate and the geometry is square planar. So this particular type of hybridization scheme allows us something, that we have taken out one of the available d orbitals from the free ion electron configuration related to the metal center. So if it is Ni2 plus, we all know it has the next element like cobalt 2 plus, so it will have 3d8 electron configuration. In case of cobalt compound, we are having 5 orbitals available to accommodate 7 electrons. Now we have utilized one of such d orbitals which are in the xy plane, because the corresponding molecule which are in the xy plane. So this is the plane which is x and y. So nickel is sitting over there, and we have 4 hybridized DsP2 orbitals. Four hybridized DsP2 orbitals, so that is why they are in the xy plane. So one is out, so we have the remaining 4 orbitals. So remaining 4 orbitals are available. So 4 d orbitals would be available to accommodate these 8 electrons. So all the levels would be filled. So that immediately tells us that the compound, which is NiCN whole 4 2 minus, which is a tetracyanonickelate species, very easily formed by the addition of cyanide ion to any nickel solution, and it therefore be diamagnetic. So this hybridization scheme also very nicely explains the corresponding magnetic property for the compound tetracyanonickelate. So as we have already seen this particular compound, we talked about the silver amine complex, which should be linear, and since it is linear, we should have the introduction of the corresponding sp hybridization scheme. So when sp hybridization is there, we have the linear ligand arrangement, and the sp hybridization will provide 2 orbitals, 2 empty orbitals, hybridized empty orbitals or vacant orbitals, to overlap with the filled orbitals of the nitrogen atom of the ammonia, and this side also another nitrogen atom from the ammonia molecule. Then we just consider what we are just talking about, the corresponding tetrachloro or tetrabromo salt or the tetrachloro cobaltate. Similar case is happening for tetrahydroxide of zinc 2 ion. Here we have the zinc center, and this is the corresponding hybridized orbital, another hybridized, another one, another one. So is sp3 hybridized one, and this is the hydroxide OH. This is OH, this is OH, and this is OH. So they will again form like tetrachlorocobaltate as the corresponding scheme for the hybridization. So zinc ion, which is already in the bivalent state, is 3d10 electronic configuration, has a 3d10 electronic configuration, and these are the vacant levels 4s and 3p levels are there. These 4 orbitals will mix together, and after mixing we get the 4 hybridized orbitals which are labeled as sp3, and these 4 hybridized orbitals will next accommodate the 4 electron pairs which are coming from the OH groups. So these OH groups, OH minus groups, basically the hydroxide ions, give each of them one lone pair of electrons to be accommodated in the vacant sp3 orbitals on the zinc center. So this is a diamagnetic compound like the free zinc ion, that means the zinc salt what we can use, the zinc chloride or zinc sulfate, which is also diamagnetic. So after this type of anionic complex formation, it remains in the corresponding diamagnetic stage in ZnOH whole 4 2 minus. So this we just have seen that tetracyanonickelate hybrid orbitals and the bonding in the square planar geometry. So if we have the corresponding square planar geometry for tetracyanonickelate, and the square plane is like this, and we have one orbital here, one orbital, and the other orbital in this side. So they basically give rise to the corresponding tetracyanonickelate species formation. So immediately when cyanide ion is reacting with the nickel salt, immediately all the water molecules, because when we are talking this reaction we talk about the corresponding hexa-aco species. So as we all know, the corresponding formation of the hexa-aco complex of nickel, which is giving hexaamine complex to the reaction with ammonia molecule or tris ethylene diamine nickel ion when it is reacting with ethylene diamine. At the same time, the hexa-aco compound, if it reacts with Cn minus, it gives, instead of any octahedral geometry, it gives the square planar configuration. So we have this particular, that means only 4 orbitals are available. Just now we have discussed this also, that only 4 orbitals are available to accommodate these electrons. So initially we have 2 electron paramagnetism on the free nickel center. So this paramagnetism from the free nickel ion is no longer available because we have forcing this particular pairing, that means this electron is pushed to this level to give rise to 4 vacant levels as dsp2, which is utilized for the corresponding hybridized orbitals which are square planar in geometry. So these are the 4 hybridized dsp2 orbitals which are pointed towards the 4 corners of a regular square, and they are next overlapping with the corresponding Cn minus groups to give rise to the corresponding tetracyanonickelate molecule. So this is the state for the 4 coordinate molecule like tetrahedral and square planar, but we have discussed so much about the corresponding coordination number of 5. So in coordination number 5, what we have seen that we can have 2 different geometries. One is square pyramidal, and other is trigonal bipyramidal. So in square pyramidal geometry, like that of the square planar compound, we can have the corresponding square pyramidal geometry of hybridization scheme is DSP2. For the DSP2 hybridized scheme, we have already seen for square planar, and we want to move from square planar to this square pyramidal. So, we put now one extra orbital. So, what orbital we will put now? One d orbital. So, this case for the square pyramidal one, because this is for square planar, the DSP2 for square planar, and when we add one more d level, one more d orbital available for that, for square pyramidal we will have D2 sp2 hybridization. So, in case of D2 sp2 hybridization, we will be utilizing one more d apart from the dx square y square. So, the new d which will be 3d z square. So, we will have 3d z square as well as 3d x square y square, and the remaining what we are utilizing for DSP2 square planar geometry. So, this square planar geometry can be transformed to the square pyramidal one like this through the addition of one d. Similarly, this trigonal bipyramidal geometry can be moved from DSP2 which was there for the square planar arrangement with the addition of one p now. So, for trigonal bipyramidal geometry, we have the corresponding hybridization scheme as this as D2 the trigonal bipyramidal one would be therefore DSP3, 1D, 1S and 3p orbitals. So, these are the square pyramidal one, and therefore, we get the corresponding two types of hybridization scheme for the trigonal bipyramidal geometry also. Next, we can go for the octahedral geometry. In case of octahedral geometry, what we can have for the hexaamine chromium 3 plus, the hybrid orbitals in this octahedral geometry can have all the 6 directions in the octahedral geometry. All the 6 directions we have the hybridized orbitals, and now the hybridization scheme is utilizing 2 d levels for the scheme and one is another 3p3. So, sp3 was known, dsp3 we know. So, now we put one more d from trigonal bipyramidal to octahedral geometry. We will utilize one more d for this octahedral hybridization scheme which is D2sp3, and we have 3 unpaired electrons in the free ion configuration. So, those 3 are still remaining with that of our compound. So, it shows 3 electron paramagnetism when we move from octahedral hybridization for D2sp3, and this is one type of hybridization where inner d orbitals are utilized. So, we consider this D2sp3 as inner orbital, hybridization, because the utilized these d levels are 3d z square and 3d x square minus y square. So, if we utilize the other d, that means the 4d z square and 4d x square minus y square, then we can have the corresponding hybridization as the outer orbital hybridization. So, both these two are possible in this particular case, where we have the other one, that means sp3d2 hybridization, and in this sp3d2 hybridization, which can give corresponding cobalt compound, a hexafluorocobaltate having 4 unpaired electrons, because all the d levels are now available for cobalt 3 for accommodating the electrons, which makes it paramagnetic and is called as a high spin compound. Because cobalt can have 2 electronic configuration, one is low spin, another is high spin. So, this particular compound where maximum possible paramagnetism is available, we consider it as a high spin compound. So, the utilized level is S, P and 4D levels now. So, utilized levels are 4D Z square and 4D X square minus Y square, giving rise to 6 sp3d2 bonds to the ligands. So, these bonds are there and these bonds are therefore giving rise to the 6 sp3d2 levels for the typical hybridization for the hexafluorocobaltate compound. So, this hexafluorocobaltate compound has therefore 4 unpaired electrons to accommodate, giving rise to 4 electron paramagnetism. This already we have seen. This is another example for D2sp3 hybridization, where we can utilize the lower, that means the inner orbital hybridization scheme, that means the lower level of D, that means the 3D levels are utilized for hybridization. So, hexacyanocobaltate can give rise to a species where all the 6 electrons to be accommodated within the available 3D levels. So, all of them are paired, and the pairing will give rise to a situation where it is a diamagnetic compound, and since the spin value is 0, we can consider them as a low spin compound. So, how we just consider the differences between the sp3d2 and d2sp3 hybrids is lies in the principal quantum number of the d level. So, what we have seen that in one case it is d2sp3, in another case it is sp3d2, which is our outer orbital scheme, outer orbital hybridization scheme. And these are from 4D level. So, we are talking something related to the change in the principal quantum number. In one case it is in the 3D level, in another case it is in the 4D level. So, we have a change in the corresponding quantum number from 3 to 4. So, in sp3d2 the sp d orbitals have the same principal quantum number, we have the high spin, and when they have the one less than sp, that means 2 of them, that means S and P are of 4th level, and one from the 3 level we get the corresponding low spin configuration. Thus, we find that a complex magnetic properties basically determines which hybrid is being used. So, when we have the magnetic moment high, that means high spin compound, we utilize the sp3d2 hybridization. When we get the low spin compound like cobalt compound, diamagnetic cobalt, which is a 3d6 configuration, we utilize the d2sp3 hybridization scheme. So, these basically gives us some idea about the corresponding magnetic moment to some extent, and all other properties which is not related to the corresponding idea of the valence bond theory. So, what we just see that in this valence bond theory, what we were discussing, that it can have certain amount of deficiencies as well, which can be rectified in the next theory what we will be discussing in our next class, which will be crystal field theory, where the idea behind this direct hybridization of the hybridized orbital and the pure atomic orbital of the ligand we will not consider. we will consider the ligand as the charges. So, it has the corresponding charge density, whether it is a neutral one or anionic one, and it can compel us for giving some corresponding crystal field splitting pattern, and that gives rise to the corresponding crystal field theory. So, there are definitely some deficiency, that is why we get the corresponding new theory, and that particular one we just consider as the different deficiencies for the valence bond approach, because it considers all the d orbitals in a complex are equal in energy, but that is not true. Depending upon the corresponding stereochemistry, the d orbitals facing the ligands differently, because some of them are along the corresponding Cartesian axis and some of them are in between. That is why they cannot have, all of them cannot have the equal energy. And the arbitrary use of 3D and 4D orbitals, just now what we have seen, that in one case as our choice we getting the 3D level, and in other case we are getting the 4D level for fixing the corresponding magnetic moment, in one case as paramagnetism and another case as diamagnetic, ignoring the corresponding energy difference. The theory is unable to inadequately explain the electronic and magnetic properties of the complexes. So, nicely it cannot explain all the electronic and all the magnetic properties of the complexes. And lastly, this is widely used mainly for the organic and main group element chemistry, so which is not very much useful for the transition metal complexes. Therefore, in transition metal chemistry, valence bond theory is superseded by the crystal field theory, what we will be discussing in our next class. And after that, we will see that we will introduce the entire molecule itself. The whole molecule will be considered in combination with the molecular orbitals. So, when we bring the molecular orbitals, the theory will become known as the corresponding molecular orbital theory, and it is often referred to as the ligand field theory, because the ligand instead of crystal, it is giving the typical field, and which is a combination of molecular orbital theory and crystal field theory, giving rise to the latest theory, which is very much useful for explaining all the properties of the metal complexes as the ligand field theory. So, next day we will just discuss about the crystal field theory. Thank you very much.